Okay, hello everybody. Welcome to Principles of Oceanography. We're going to be talking about the material in Chapter 10, but I wanted to cover a couple of things before we get started. So let me put this screen away and bring up the syllabus. So here we are, week 8. We didn't quite get to the chapter on waves last week, so we'll be covering that this week. And most of the chapter material that we cover will be about the chapter 10. Now, I'm not going to cover chapter 11 in as much detail, but we will touch on tides, tsunamis, etc. What you do need to know is that there'll be a midterm next week. And the way we structure midterms is that there'll be a take-home midterm with many questions. I think it's about 140 multiple choice questions. And the questions will be provided with references to the portions of the textbook where you can find a discussion of the topic covered by the question. So that by answering these questions, by consulting the text as you go through, this is an excellent way of preparing for then what will be a in-class version of the midterm that we offer, that will be offered a week from today. And in that midterm, you'll have a selection of the questions or similar questions as to the ones that were on the take-home. So the take-home midterm will be available on Friday, and then it will be due on Monday, and then on Tuesday, the 2nd of March, we'll have the in-class midterm. Okay. I also wanted to say that just to avoid stacking up too much work and allowing you to focus on the midterms, we'll be doing the revisions to the milestone 2 work, which has been graded. And so there'll be an opportunity for doing those revisions and fixing up the points in each of the submissions that were indicated by Carrie or myself in the grading. Okay, any questions about that midterm take-home revision of the milestone 2 submission? Questions? Everybody's got that? Everybody raise their hand?
All right, babe, I just joined class.
Yeah, and I'm going to cover a lot of the material today, but then
I also have a notebook, 2 notebooks, a book, and my iPad if you want any.
can't quite hear you. Sorry. Say it again.
And a bunch of crystals.
Daily
Cool.
So I did it this morning. It tells you prompts.
Oh, nice, babe.
Every day.
What prompts? I also have an app.
It was like,
Okay.
I think it's real fast. What am I grateful for today? What am I looking forward to today?
So,
Mr. McDonald,
yeah.
is there a quiz today that you posted at 12?
Yes, I did. And there's a video. So we're going to cover some of the introductory stuff on the waves. And then I'm going to let you break into, I'll show you a video, and then you'll break into your group and answer the questions on the quiz. Okay?
Gotcha.
Okay. So, all right. So I want to move along so we have enough time to watch the video and cover the material. So are there questions about the midterm? I want to make sure everybody's prepared and understands that that's going to be.
Yeah, I got a question. You said that we're taking the midterm home on Friday. When is it going to be due?
It's going to be due the following Monday.
Okay.
Okay. So the quiz will be opened up on Friday, and you'll be able to work on the questions over the weekend. You'll hand that quiz in on Monday, and it's going to be multiple choice and some essay questions. And then on Tuesday, there'll be an in-class version of that quiz, okay? So the idea of the midterm is to ask a whole series of questions And in answering the questions, you'll have a chance to go back and look at the reread and think about the portions of the text where the topics covered by each question are presented. So there's a reference to page numbers and sections and so forth that'll let you find the answers, but hopefully in the process of finding the answers, you'll get to understand the material. Okay?
Will we be able to use the take-home midterm on our in-class midterm?
Will you be able to use it?
Reference it.
That's a good point. No, you won't be able to use it because it's going to be submitted through Canvas.
Oh, okay.
So yeah, that would be a little too easy, wouldn't it? Okay. So any other questions?
Is chapter 10 going to be on the midterm?
Yes, the material today will be on the midterm, definitely. Okay, let me get started then. So I will. All right, so that's the homework and the midterm, and the material we're covering are waves and tsunamis. And tsunami is a type of wave, a special type of wave. And so let's go through that material. First, I wanted to show this graphic, and this is talking about the Coriolis effect. And I think this sort of has come up a number of times. And this is just the cosine function showing how the Coriolis effect is influenced by a latitude. So at 0 degrees latitude, the Coriolis effect goes to 0, and then it increases steadily as a sine function or cosine function as you go further and further north on the planet, on the surface of the Earth. And so the material that we covered in terms of deflection of ocean currents and ocean waves responds to this Coriolis force. And so this is just a graphical representation of how that force, a rightward deflection in the northern hemisphere and a leftward deflection in the southern hemisphere, how that is dependent on the latitude, as a reminder. Okay, so the big ideas about waves are that they transmit energy across the ocean surface. And that energy can come from a number of different forces, seismic events, the gravitational attraction of the moon, principally the frictional force of wind blowing across the water, but basically any disturbance of the ocean surface creates energy, which is then transmitted across through this medium of the water body. And there are different ways that we classify oceans and classify waves in the ocean. And a lot of these depend on the relation between ocean size, water size, and wave size, and water depth. Surf, which we'll be looking at in the video that we watch, is caused by friction of a wave when that wave energy interacts with the sloping bottom. So energy is transferred from wind to water, and that waves can interfere with each other, and they can interfere and react to solid objects. Of course, an example of a solid object would be the sloping bottom. So there's a huge difference in the waves that we see as they break and as they come onto a beach, and then the ways waves behave when they're out in the open ocean and are not being affected by frictional interaction with the bottom. So here's a diagram of all the different types of waves that we've been talking about, and they're classified here according to the disturbing force, the restoring force, and the type of waves. Disturbing force. Okay, well, I said that waves transmit energy, and this energy is created by this disturbing force. And so for most of the waves that we look at, the disturbing force is the wind. Okay, well, what do we see when we look at wind? And this is the range of wave period. That's the distance between successive wave crest as they pass a fixed point. So wind affects water motion and waves and wave development across a wide range of time periods. Other disturbing forces, as I indicated, are seismic disruption, landslides, anything that's sort of, if you think of a disturbing force as being sort of an instantaneous event, think of throwing a rock into a puddle of water, a pool of water, and that disturbing force creates energy which radiates outward in that series of ripples. Okay? And then the disturbing force in terms of gravity can be a disturbing force, as we'll see when we look at the influence of the moon's gravity and the sun's gravity on the movement of water across the planet. And so these are the disturbing forces. And then the restoring force. Well, the restoring force is, so there's a disturbance, the wave, the water is lifted, and then the restoring force is the force that pulls the water back, that sort of resists the energy. And that restoring force for most of the waves is gravity. So gravity is the restoring force. However, for small waves, very tiny waves, the restoring force is not so much gravity as it is surface tension, the tendency of water to resist changing height. And the types of waves that we classified here, so gravity being disturbing force for the longest waves, these are tides. Then seismic disruption we can think of as tsunamis. And a sesh is a particular sort of wave which is generated sort of a standing wave, and it's when water is rocking back and forth within an enclosed basin. Sort of the way would happen if you got into a full bathtub and settled down, you'd be disturbing force, and after you sat in the bathtub for a while, the water would rock back and forth until it finally stabilized. So that's a particular sort of wave called a sesh. And then wind waves are the waves that are most familiar to us. These are the waves that are traveling, the energy traveling across the ocean generated by friction of the waves. And then finally, the smallest waves are capillary waves. These are sort of wind ripples. And these are waves that have a relatively tiny wavelength, a few centimeters. And these are the kind of waves that we see when there's just a bit of wind blowing across the surface, and we see that sort of roughness of the surface water. Those are capillary waves or small waves. Okay, so this is a classification of waves according to the disturbing force and the restoring force, and then we give different names to waves according to where they lie within the spectrum of wave energy. And this diagram shows the amount of energy in the ocean surface, and we can see that for most of the ocean, the largest amount of energy are in these relatively long waves, wind waves. And so the period here, period period in seconds for two successive waves to pass a fixed point. So wind waves with a period of about 10 seconds comprise most of the energy in the ocean surface at any given time. Okay, so just to reiterate, energy is being transmitted by the waves, but water itself is not moving laterally. It moves up and down as this energy passes through. And it's maybe a little counterintuitive to think about, but the water is not actually moving, at least not very much. There's some exceptions to that, and I'll cover that in a second. And so we can think about that in terms of a floating object. As the wave passes through, the object is lifted, the energy is passing through, and then so initially the floating object rises up, and then as the energy passes through, it begins to sink down. And so the net path of any object or any parcel of water within that wave is an orbital path, a circular path. And we think of waves in terms of sine wave functions, and they're pretty frequently drawn that way. But as these orbital paths pass across the ocean, because there's an interface between the water and the air, what we see are crests. But if you look at the motion of any object or any parcel of water within that wave, it's going to follow a orbital path without moving. So there is no sort of net transfer of lateral transfer in the direction of the wave. Only the energy is passing through. And now this analogy doesn't explain all the varieties and features of waves, but this essential point that energy is moving through the water, not the water itself, is a key factor to keep in mind. All right, I've touched on these a little bit, and but let's go through and define our terms a little bit better. So the major terms are, we describe sine waves, not wind waves. So sine waves behave in the same way as wind waves in terms of the orbital transfer of material, but they have a very different appearance. And so the wavelength is the distance between crests. So crest to crest or trough to trough, both of these lengths are equal. These are this is the wavelength. Okay. The height of the wave is the distance from the trough to the top of the wave height. And so this is essentially the diameter of that orbit is the wave height. Okay. And this is the orbital path that everything follows. Okay, and then a couple of other periods, things. The frequency are the number of wave crests passing point A or point B in each second. And the period is the time required for the wave crest at point A to reach point B. So we can think about a period, as so wavelength, wave height, period, and frequency. And I'm not going to go to this site, but you can play around with some of these parameters of wavelength, wave height, period, and frequency if you follow this link here. And there's a page that lets you, this sort of a calculator and a graphic representation of sine waves or cosine waves that lets you see what happens when these parameters of waves are varied. Okay, so we can classify waves in terms of the disturbing force, and we already seen that. And then we need to distinguish between free waves and forced waves. So a free wave is one which is continuing without more energy being added to it. And the example of that, would be the waves that are generated when you throw an object into the water, or if there's a seismic event, but there's a single disturbing event, something that displaces water, and that displacement generates energy, which is transmitted outward from the source. But the important thing is that that's a finite event. So even after the stone is thrown into the water, the ripples continue freely to transmit that energy further. Now, forced waves mean that there's ongoing reinforcement, so that there's always some force being applied. And so we can think of that as waves that are generated in the ocean by wind. If the wind continues to blow, the waves actually can build up and get higher and higher over time, but they're being forced by this continual input of energy. Okay? Now, that doesn't mean that if you can generate waves with wind, and then the wind can cease and the waves will continue. So, and this is something that we'll see in the video, that free waves can be generated from a storm far distant and arrive at a point that's not experiencing those storm conditions. Okay. So here are different types of waves classified, and we've already seen this a little bit in terms of the wave type. So wind wave, the typical wavelength is 60 to 150 meters, something like 200 to 500 feet, and the disturbing force is wind over the ocean. The sesh is the typical wavelength is large, hundreds, thousands of meters, and it's a function of the size of the basin, the size of the tub within which that water is occurring. And the disturbing force can be changes in atmospheric pressure, can be a storm surge, a tsunami, a landslide. So you can think of like a long, narrow lake. Lake Geneva, for example, experiences seshes when wind builds up the waves at one side and then stops, and then the water rocks back and forth within that. So a sesh is an example of a variable wave. Seismic sea waves, tsunamis, have very long wavelength, 200 kilometers or longer. The disturbing force are sudden shifts in the seafloor due to an earthquake, a volcanic eruption, a landslide. These are all events which can generate tsunamis. And then a tide. So a tide is always a forced wave because the gravitational attraction of the sun and the moon are continuous. So the wave is always being driven by that gravitational force. And it's also influenced by the rotational properties of the Earth and also Coriolis effects and so forth. So the typical wavelength of a tide is very, very long. Half the circumference of the Earth is the typical wavelength of the wavelength of tide. Okay, so these are ways of classifying waves. All right, well, we're going to look at a more complete wave catalog, some additional names that we see. So ripples, wind waves, and swell. These are all due to effects of wind on the sea surface. Now, there's also, so far we've been talking about waves at the surface and looking at crests of waves and thinking about things floating, but you can also have internal waves. So remember we talked about the thermocline and density interfaces within the water column. Well, energy can be transmitted along those interfaces, and there can be very long period waves within the ocean. Often these are referred to as Rossby waves, and so they can occur at depth. And there are wave effects that are noticeable and can be measured, not just at the surface of the ocean, but downward in the water column. Tsunamis, again, generated by seismic disturbance near the shore. Rossby or planetary waves, these are large scale and long period, and they're due to instability in these pressure gradients. So, the internal waves that occur within the water column, these are often classified as Rossby or planetary waves. And then tides, and this is due to the fluctuating gravitational forces of the sun and the moon. And we'll see when we talk more about tides that as the moon orbits the Earth, it's going to apply its attraction in different areas, and then as the Earth rotates on its axis against that gravitational force, then that force is expressed in terms of this large wave. Okay. All right, well, let's talk about, we're going to talk about wind waves, and then we're going to talk about capillary waves, and then how waves develop in the shore. All right, so we can think of waves beginning, so the beginning of a wave starts when the wind drags on the surface of the water. And within the smallest waves have a maximum wavelength of about 1.5 to 2 centimeters. So the maximum wavelength of about 2 centimeters. And these are the restoring force is gravity and capillary and these are the restoring force is surface tension in the water. And so the wind forces, as the wind continues to blow, the friction of the wind is going to be most felt at this higher acute angle, and that's going to cause these waves to increase in wave height, and they'll slowly build up from capillary waves to wind waves. What do I mean by capillary waves? Well, let me illustrate with this picture. So this is a picture that I took many years ago, and we were offshore in the Gulf of Mexico, and we were over a natural oil seep. So there was oil rising up from the bottom of the ocean, in this case about 500 meters down, and reaching the surface. And when that oil reaches the surface, it forms a thin layer, microscopically thin layer, which has the effect of dampening out these capillary waves. And so, here you're seeing these little crests, and there's a typical wavelength of about, I said it was about 1.75 centimeters. So you can see that here's a Coke can floating in the water, and that gives you sort of a sense of what the general wavelength of these waves was. You can also see that these waves are sort of building up, and there's a bit of a swell building. Okay, so this is the unoiled water where the wind is generating these little ripples or capillary waves. On the other side of the ship, where the oil was coming to the surface, I took a picture in the same, with the same conditions, sun glint and everything, with another Coke can for reference, and you can see that the wavelength is much longer, so that the ability of the water to deform was altered by this thin layer of oil floating on the surface. So you said the restoring force of the water is the restoring force is the surface tension of the water. Well, if you add the surface tension of the water, the elastic properties of this thin layer of oil, the restoring force is even more powerful, and that means that the wavelength for these capillary waves, these ripples, is much longer, and you can see that distant difference here. Now, interestingly, this is one of the reasons that we're able to see oil floating in the ocean. So, if you have a patch of oil, the oil appears bright because these little ripples are wider or long, or there's a greater wavelength between the ripples, and so they tend to reflect sunlight. So the sun glint coming in reflects more acutely off the surface. This is called specular reflection. So there's specular reflection of a patch of water with floating oil on it is greater than the surrounding water. Come back and see this. So you can see that the light energy bouncing off the surface is scattered, and you have light patches and dark patches because the wavelengths of these capillary waves and the wind ripples are much shorter than in the area where there's oiled water. And so the darker water here, same conditions and everything, it appears darker because the light energy is scattered more broadly than it is in the oiled water. So there's a specular reflector on the surface created by that thin layer of oil. And the area appears bright. And so here's an image where the reflecting energy isn't sunlight, but it's radar energy. And so this is a satellite synthetic aperture radar satellite that is energizing the water with radar energy. And here the patches of floating oil are causing the radar energy to be reflected away from the satellite sensor. And so these patches of oil appear dark. This is quite a large scale image. It's probably about 15 kilometers from side to side. So these are large oil slicks, and they're being visualized because of the dampening of capillary waves within these areas. And then you can see that the surrounding water appears brighter because the backscatter reflects more energy back to the radar sensor. Okay. So what are the factors that affect wind development? We started by making these capillary waves, and we said that they're, they have a maximum wavelength of about 1.75 or 2 kilometers. And so as the wind blows across the ocean, assuming that you start, with a wind and that blows steadily over time, the wave ripples first develop into sort of a choppy appearance, as the crests of these capillary waves are pulled higher and higher by the continuing friction of the wind. And over time, the waves will build higher and higher as more energy is transmitted into the water. And over time, the fully developed sea, these fully developed waves, build together as wave trains, and this is what we call swell. So the factors affecting this are, of course, the strength of the wind, and then also the length of the fetch. That's the distance of water over which this wind energy is being expressed. And so, the ability of waves to build up in the ocean depends on how long the area is, how wide the area is over which the wind is blowing. And so if you think about that, if you had a swimming pool and with a very powerful wind blowing on it, well, you might create froth and waves and so forth, but no matter how powerful the wind was, you wouldn't build up huge waves within a swimming pool. There's simply not enough fetch, not enough distance for that energy to be fully absorbed and transmitted by the water. But if you increase that swimming pool to the size of a lake, well, you could build up waves within a certain area, to a certain height. But even within a lake, the width of the lake or the length of the lake over which the wind was blowing would limit the size of the waves that could develop in that body of water. Of course, if you go out into the open ocean, the fetch is can be sufficiently large for big waves to build up. But even within, even in the ocean, if the storm is located, offshore, the distance over which that wind energy is acting will determine how large the waves become. So we can classify this, the wind strength. The wind must be moving faster than the wave crests for energy transfer to continue. Winds that blow for a short period of time will not generate large waves. But winds that blow for a long period, the fetch is the uninterrupted distance over which the wind blows without changing direction. So the strength of the wind, the fact that the wind continuously blows, and then this fetch, the length of the ocean over which this wind energy is acting, these factors combined will determine how large the ocean waves are. Okay. Well, ocean waves are, the waves that are occurring out in the ocean are, as we described, the water particles, water parcels are responding in an orbital fashion to the transmission of energy. And so these orbital waves are waves in which the particles of energy move in closed circles as the wave passes through any fixed point. Progressive waves are waves of moving energy in which the waveform moves in one direction along the surface of the transmission medium. Orbital waves are a type of progressive waves because the waveform moves forward. What does that look like? Okay, so note that the water molecules, you know, in the water crest move in the same direction of the wave, but the molecules in the trough move in the opposite direction. Okay, that makes sense in order to complete this orbital path. So as the wave moves through any particular point, as it builds towards the crest, the water is moving in the same direction as the wave. And then as it goes into the trough, it reverses direction and brings the water particles around. Okay? So that's the, you know, that describes this, that's what this cycle of moving with the wave energy and then against the wave energy for any particular point is what describes a circular path. Well, the energy that's occurring at the surface of the water, that's transmitted downward by the friction of the water acting on water below the surface. But that frictional effect is dissipated as you get deeper and deeper into the ocean. So at about half the wavelength depth, the water really begins to disappear. So at about half of the depth, so if we said that here's our wavelength from here to here, at about half of that wavelength, the energy is almost entirely disappeared. Keep that in mind, that half wavelength, this depth, because one of the important factors of waves is how they interact with the bottom. And we're going to be looking at a video that shows what happens when waves break on the shore. And the motion ceases at this half wavelength depth will determine when wave crests begin to build up because they're rubbing against the bottom, they're filling the bottom. Okay, so you know, ocean waves develop within a fixed set of limits, and that's controlled by the viscosity of water. So water is a medium with a particular viscosity. And you think about if you had an ocean of honey, we would have very different waves. On the other hand, if we had an ocean of alcohol, the waves would be able to have you know, much higher wave crests. So the viscosity of the water, the viscosity of the medium, is what determines what the wavelength and the wave periods will be under different disturbing forces. So most of the wavelength in the ocean has a wavelength sort of in this range here. So wavelength of 0 to about 250 meters, and velocity in seconds of about 19 meters per second to about 30 meters per second. So now we talked about what happens. So let's imagine a storm blowing across the water. So we have wind speed in one direction, and it's blowing at about 19 kilometers per hour, 12 miles per hour. So the fetch is 19, and we assume that the fetch is 19 kilometers, the wind duration of 2 hours. The average height of the waves is going to be just about 1/4 of a meter, about a foot. And the average wavelength will be about 28 feet. And the average period, the number of waves crossing a point at any one over any period of time, is going to be about 3 seconds. So a wave will pass a point about every 3 seconds under these conditions. If we increase the wind speed to 37 kilometers per hour, 23 miles an hour, so that's a good stiff breeze. And then the minimum fetch is 139 kilometers, and to fully develop into a, you know, for the waves to build as big as they can. I guess let me back up and say that, you know, when the wind begins to blow, of course, the waves are not as big as they can be, but so there's a limit to how large these waves can be, how fast they can move, and that limit is set by the wind speed, and then also the distance over which that speed is acting. So for a 37 km/h wind, it takes a fetch of at least 139 kilometers for this sea to develop to its maximum height. So the average height of under these conditions would be about 4 feet, 5 feet, 1.5 meters, and the average wavelength would be about 34 meters. Period, 37 seconds. Okay, and then we can increase the wind speed incrementally here. So when we get to a very powerful wind, near a hurricane force wind, such as you would have in a pretty severe storm, the fetch, the distance of ocean needed for that for the waves to build up to its maximum height becomes much larger. Almost 1,500, 1,633 miles, 2,600 kilometers. And the time it takes for the sea to build up is much longer, 70 hours in this case. The average height can be much greater. So here we're talking about truly monstrous waves, 14, 15 meters high, nearly 50 feet in height, and a very, very long average wavelength. Keep this wavelength in mind, and remember that the wavelength, is dissipated at about half of the wave height. The energy of the waves dissipates at about half of the wavelength. So if you were scuba diving with a fully developed sea, you could feel the effects of these waves down to about 30 feet. Okay, but below that, you wouldn't feel the effects of the waves. For this huge storm, you could feel the effects of the waves all the way down at nearly 700 feet. Okay, or half of that distance rather. So that's saying that these very large waves here, 14 meters in height, that would at half this distance, they would begin interacting with the bottom. Okay, so that's important. So we talked about waves developing into swells, and what happens with waves is they don't behave as individual entities. They tend to join together in trains, and the fastest waves, the ones that are higher, move fastest and leave the area of wave formation sooner. So this undulation of and this creates this sort of a pattern of waves within any period. And this undulation of ocean water caused by the dissipation of waves, dispersion of waves, is the swell. So to the left, we have this wave train. And so this is the distance moved by the wave train. And then this is the distance moved by the individual waves. So we can see that this parcel of energy is being transmitted in this group of waves. The fastest waves are moving through the group more quickly. So, here is, this individual wave has already moved through the wave train. And so we can see that and these swells can also be described by wave functions, waves made up of multiple waves. Okay, so there's some ways that we can calculate. We can use these parameters of waves to try to understand how waves are moving. So we can think of wavelength. So the speed of waves, also called celerity, is a function of wavelength and wave period. Remember I said the wavelength was the distance crest to crest of waves in a particular sea. And then period is the number of waves passing a fixed point over any length of time. Now, to put this in human terms, we can think of wavelengths as steps. So what's your average step? If you take about a stride that's about 2 feet, if that's your average wavelength, then the number of steps per minute are going to determine how fast you go, or number of steps per second. So if you're traveling at length of your step is say 2 feet, and you're making 3 steps per second, you're going to be moving 6 feet per second. That makes sense. Okay. Then you can also classify this in terms of gravity, and this, because of the orbital behavior here, we can divide everything by. So you can also calculate this in terms of 1.25 times the length, square root of that would give you the celerity. So, okay, let's skip over that. So let's think about the difference between deep water waves and shallow water waves. So that a deep water wave, there's no interaction of the wave energy with the bottom, the ocean's floor, because the depth is greater than half of the wavelength. But as the wave approaches the shoreline, the depth increases. And so as the depth increases, the energy of the passing water is dissipated by this friction, and the dissipation tends to elongate these orbital paths. And with this elongation, you get this increase in height of the waves. So, in the ocean, I don't know if anybody's been offshore when there's been really, really high wind. You see waves breaking offshore. Those are white caps. And so when the breaking angle is less than 7 across, the waves will begin to break. And so this is the maximum height according to the wave height. So when this height is less than 7 across, the waves will break offshore. As wind waves approach the shore, they can break in different ways. And so plunging waves break violently against the shore. And there's like an air-filled tube or a channel between the crest and the foot of the wave. Plunging waves are formed when waves approach the shore that over a steeply sloping bottom. Okay? And so this plunging wave are what surfers in particular look for. They look for an abrupt change in the bottom, which causes the water suddenly to build up and then plunge over. And that plunging over is what creates the nice break that surfers look for. And now if we think about this a little bit, we can see that the height of the waves, as a function of the energy that's developed the waves, and the depth of the bottom are going to produce different waves under different conditions. Okay. So, this is sort of a diagram of how that occurs. And so we have here in the open ocean, these are waves. The wave depth is about half of the wavelength here. And so that begins to stretch this out and to steepen these waves. And then as when the ratio of wave height to water depth is about 3/4, then the waves begin to break. And so this a spilling wave then is what occurs when there's a sort of this gradual breaking. And that's what you see, when you're on the beach, around here, when you see waves that come in and they break and there's this sort of crest, those are spilling waves. And they're caused by this gradual decrease in water depth as the waves approach the shore. Okay, so there's other topics in this that I'm going to talk about, but I'd like to go ahead and move ahead and we'll just look at our video. Let's see, so get it into the right place. And so we'll watch this video and then you'll be able to, oops. Where's my video? Hang on, I'm having trouble getting the video to play here. Let's see. There we go. So this is in Hawaii. And here we're seeing waves that are suddenly breaking. These are really huge waves, and we'll talk about why this occurs. Okay, I think I'm in the wrong place here, so bear with me a second, and I will. Okay, here we go.
January 28, 1998. Under blue skies and light winds, some of the biggest waves ever recorded hit the Hawaiian Islands and set the stage for surfing history. For the few people who make it their destiny to find and ride the biggest waves possible, it was the perfect storm. But authorities would declare it illegal for anyone to enter the waters.
Everyone's gonna die. The guys out there, it was just completely unsurfable.
Still, some were determined to test the awesome powers of the ocean. It was a day nature, technology, and sport came together, and a few surfers explored the boundaries of their fear and craving for adventure. In January of 1998, the National Weather Service announced that a storm off the coast of Japan was headed directly for Hawaii and would produce some of the largest waves ever recorded. The weather reports indicated that the approaching waves may be big enough to take out roads and destroy homes all along the north shores of the Hawaiian Islands.
The National Weather Service posts a high surf advisory when the waves are expected to be 10 feet or larger on the North Shore. Whereas when they get really big, like 25 feet, we call that condition black. And in that case, the Civil Defense calls the alert, and they actually go out to the North Shore or to the North Shores. They close roads, they have sirens, they alert people, they tell them to get to high ground. They basically save a lot of lives.
Condition.
Here on the ATM, Hawaii Buoy report.
Large surf always pounds the north shores of Hawaii during the winter months, but no one had ever dreamed of surfing waves as big as those said to be on the way to Hawaii on January 28, 1998.
We get very, very intense winter storm systems in the Western Pacific that produce unusually large swell. So Hawaii is uniquely positioned to get very large waves. It's the island group that's furthest away from any major landmass on the planet. Essentially, it is the action of the atmosphere wind on the ocean that produces the wave. There are three factors that are important. One is the wind speed, naturally. The stronger the wind, the greater the potential for large waves. The second is the fetch, or the distance over which the wind is blowing, producing the waves. And the third is the duration that the wind is blowing over this area.
Swells are recorded and reported daily by the National Weather Service. Richard Grigg is one of the world's most respected oceanographers and a professor at the University of Hawaii. He is also one of the great surfers of the 20th century. His big wave riding is the stuff of legend.
What determines the shape of the wave is the shape of the bottom. If the bottom is gradual, the wave will come in and spill or crumble off the top. Whereas if the bottom is abrupt, you have a shelf, the wave will come in, hit that shelf, the energy is suddenly and abruptly concentrated upward. It becomes very steep and very unstable all at once and throws out in a plunging manner, and you have a top to bottom breaking curl. And that, of course, is the ultimate for a surfer, because that's where you want to be, in the curl. As far as monitoring the waves, we have a buoy system in the Hawaiian Islands. In fact, there are 4 buoys, one north of Kauai and then 3 on the southern shores about 200 miles out. These buoys record the motion of the ocean. As the swells go by, they're lifted up and then they fall in between the crests and the troughs. Now that data is radioed and also sent by satellite back to the National Weather Service.
These reports provide general information to the public about daily ocean conditions. They also alert island residents to extreme weather phenomena, such as tidal waves and tsunamis. Surfers rely on this data to predict upcoming swells. 1998 was a year like no other for surf. With El Nino in full swing, the northern hemisphere was brewing up some of the biggest storms of the century. But no one was prepared for the weather data that came in on January 27. It was so unbelievable that many thought it was a mistake. A massive storm off the coast of Japan generated monster waves that were destined to hit Hawaii the next morning. The storm itself would pass within 1,500 nautical miles of Hawaii. The swells generated would travel across the open oceans until they reached the north shores of the islands, where ultimately they would release their energy. Ironically, the weather forecast was calling for clear skies and light winds.
It was Hawaii's perfect storm. This is known as one of the 2 largest swell events we've ever had in Hawaii. That is, ever meaning the last century, over which records have been kept. We had a storm with winds of 65 knots, blowing for 36 hours over a 1,000-mile fetch directly at us.
The buoy showed a period of 25 seconds and wave heights over the open ocean of 28 feet. Now, the National Weather Service, through a formula that they've developed with the data, calculated that the waves at the beach would be 44 feet.
Wave heights of 44 feet would produce wave faces in excess of 80 feet, the height of a 10-story building. In 1969, massive waves of 40 feet or even higher took out beaches, roads, and homes all along the North Shore. There was concern that this storm could produce even bigger waves than in 1969.
State civil defense crews spent the night and early morning warning motorists of hazardous road conditions as high surf washed onto Kamehameha Highway. No one knew how large the surf was until first light.
Thousands of spectators lined the beaches, roads, and shoreline around Waimea Bay in anticipation of the Eddie Aikau contest. Surfers.
Waimea is an absolute death cauldron once it goes over 25 feet there. And this was 35 to 40 foot surf. You had all the best big wave riders in the world sitting there going, I don't think so, man. I don't think so. It was crazy.
When a wave stands up all at once and breaks along a long stretch, it is said to have closed out.
Every 3 minutes, there was a 35, 40 foot closeout set. And I just looked at it and I just thought, these guys are kidding. Like, how can they be thinking of holding this thing? You know, like everyone's going to die and it goes out there. It was just completely unsurfable.
There's so much water pushing into a small bay like that. And even rescue attempts can't help you. So you're taking your life in your own hands.
Finally, after 4 hours of staring at waves that were impossible to paddle out to, the contest was called off.
A rarity in Waimea Bay today. Waves too big for the biggest big wave surf contest in the country that has surf's biggest first place payday.
But not everyone on the beach was willing to give up the day. A handful of surfers had already hatched their own plan to get out there with their jet skis and access these monster waves. But the Extreme Film crew launched their helicopter to take pictures of a rare and beautiful sight, with slim hopes that someone, anyone, might make it out to the one spot that was surfable, an outer reef, half a mile out, in 50-foot deep waters, at a break called Log Cabins.
At Log Cabins, the shelf out there is quite steep, but it's deep. There's a break around 50 feet that drops to 60 feet, about a 10-foot shelf. And that's what actually triggers the wave to break. Now, when it's 25 feet, it's not going to break out there. That's too small. And so it goes right over that shelf and it goes up a little bit and then doesn't break and comes in. However, when the surf is like 40, 45 feet, it hits that shelf, goes top to bottom and breaks.
In all, 12 people made it through the treacherous breakwaters to the open ocean that day. What they saw once they got there was beyond comprehension. Mammoth swells as wide as football fields, with tubes big enough to fit a house.
It was absolutely the most amazing sight I've ever seen in surfing. The waves looked as big as like 10-story buildings.
And there, ready and waiting, was the Extreme Film crew in their helicopter. Now the only question was, were the waves too big to ride?
The waves looked kind of otherworldly. You couldn't really tell how big they were. And then when people started dropping in, everyone's mouth just dropped. I mean, we were aghast. But to see these tiny figures on these mountains, it never happened before.
Peter Cole has been living and surfing on the North Shore of Oahu since 1958 and has witnessed much of surfing history.
I was witnessing the most fantastic display of surfing and maneuvering in big waves I've ever seen in my life. And these guys are doing all these turns on these giant waves. You don't even think about big wave riding. It doesn't look dangerous at all. It looked like they were just having fun.
After successfully towing into a handful of perfect waves, Ross Clark Jones and Tony Ray found themselves in the worst situation imaginable. They were chased down, running for their lives from a monster wave that was moving faster than they were.
I towed Ross onto the wave and looked like we're in the perfect spot, but the wave just kept building and getting bigger, and all of a sudden I realized that the wave was actually sucking me back into it. My equipment wasn't fast enough.
It's a very unpleasant thing being mowed over by, 40 feet of white water. I just remember looking behind me and just seeing this huge wall of white water.
I realized it was going to get me, but I was still trying to get out of the situation. I was like, head down and just go as fast as I can. The biggest danger was the ski hitting me. It's a 500-pound piece of fiberglass and metal that's going to hit you in the head and could kill you in a second.
I had a few seconds to try and get a full lungful of air. I got that lungful of air and I was still riding in this, just enveloped in this white screen of foam, and I was actually riding for a little while. I had time to release that breath and get another breath. I did it a third time, and then finally eventually smashed me and threw me around like quite violently.
I was hanging onto the ski, the wave blasted me, and I hung on as tight as I could, and it just disappeared. It was like it evaporated from under me. I didn't know where it was, and I was flying through the air for it seemed like 20 seconds before I landed back in the ocean and got pummeled by the wave.
I was waiting for Tony to pop up, and he hadn't popped up anywhere, which was quite frightening. I was frightened for his life. A few seconds later, he popped out, and he was actually further out than I was. And yeah, it was an experience.
The worst place to be is at the point where a pitching wave hits the surface of the bottom of the wave. That is the place where the full force of the wave explodes on itself. No one came closer to that place on January 28th than Noah Johnson.
Shape of the wave was really good, really hollow, and it looked like it was going to be exactly what I'd been after, It ended up being so big that my board wasn't making enough headway down and across the wave. And I just was doing everything I could to get my line going where I needed to go, and I just wasn't getting there. When you fall in or around the lip, it can be dangerous. So I turned down the wave, started trying to get away from the lip. I didn't want to land on it. And I ended up timing it just about as good as I possibly could have because the thing hit the back of my board and my back foot. It wasn't quite close enough to me to knock me down. I ended up being able to ride out the initial explosion. The thing ended up just plowing into me, moving me off my board, and just sent me spinning for one of that washing machine cycle. And it was going to be the worst wipe I'd ever had to deal with. I stopped spinning and tumbling, and the water calmed down. And my partner Aaron was right there. He's right there to pick me up.
North Shore local Aaron Lambert was one of the lucky ones who made it out that day. He was the only one who was actually able to get inside one of these massive barrels and ride out of it. Troy Alovis experienced the worst wipeout of the day.
There was a wave that came in that I was looking for out there. Got towed into the wave, and I was making some S turns down the face of it, and I was thinking I'm going to get deep in this barrel. And as I came off the bottom and saw the wave crest and bowl over me, I was standing in this barrel that was so huge and massive. I was shocked. And I thought, I'm going to just try to pull through this thing and see if I can penetrate through that. You know, hopefully the curtain's not too thick. And when I hit the curtain, it was all over with. My board broke right in half underneath my feet. I ended up in water that was so black I couldn't see which way was up or down. And I knew that there's going to be a wave behind it sooner or later. And I just started making strokes towards the surface. And when I got to the surface, I was looking at the shoreline of the North Shore, and I saw the mountain range above Pupacan Mountains, and I thought that was the next wave. Turned around and looked, and there was another one coming down on me right then. Luckily, I got a good couple breaths of air, and I got beat again and got pushed in a little further. I took about 20 more in the head right in a row there. And then Noah J came and got me, and I went back out.
A milestone in the history of surfing was set when Dan Moore towed Ken Bradshaw into the biggest wave of the day, what many say is the biggest wave ever ridden.
Dropping him in and following out of the shoulder, looking back and seeing the wave behind him. He didn't see it. He didn't see what I saw, but it was the biggest. You know, you could have fit 2 houses into this tube.
If it happens to be true, and it seems to be holding true, under scrutiny of all our peers and my peers, that I have ridden the largest wave ever ridden by a human. That's pretty cool. That's pretty neat.
Okay. So we didn't have enough time to break into groups, but I've changed the due date for this quiz till midnight tonight. And in the module, you'll see a link for the YouTube video. You can go back and look at that if you want to catch this. And then there's a series of 10 questions. It's permitted to work on this in teams if you like, or you can do it individually, but everybody will be graded individually for answering these quiz questions. Okay, so that's the end of class for today. We'll finish off on waves and talk about tides, start talking about tides on Thursday when we're back together again. Are there any questions before we adjourn? Okay, so no questions. There's a quiz in the module. Everybody has to answer those quiz questions. The answers to the quiz can be found in the video, combining what the information given in the video with the material that we've covered in lecture today. And we'll continue with our lecture on waves and start talking about tides on Thursday. And then on Friday, of course, the take-home midterm will be available to help you study over the weekend and prepare for the in-class midterm 1 week from today. All right, any questions? No questions? I will end the class and hope that you enjoyed that very cool video. All right.
Really quickly, can I ask you a question?
Sure, absolutely.
I sent you an email, but I thought it might just be easier just to ask you now, take less of your time.
Sure.
I have so much studying and like a ton of midterm stuff to do over the weekend. Would you be open to opening the take-home midterm early so that I can go ahead and get started on it? Or
it's a thought. I guess I can do that.
That would be so helpful.
Okay. All right. I'll do that. I'll open it. I'll have to go in and monkey with the due dates. Are there other folks that would like to get started on the midterm early as well?
Me.
Okay. All right.
Me too.
Yes,
All right.
please.
All
Thank you
right. All right. Well, I will open them up at midnight tonight then. So I want you to get done with the quiz. Fair enough. I'll make the midterm available. I'm not going to answer questions about it in class on Thursday, so you need to be working independently, and then we can talk, and then we'll have it on Tuesday. It'll be doing.
Okay. Also, when are the revisions for milestone 2 due?
After the midterm. I don't want to get in the way there. And the revisions, looking at most of them are pretty minor. So you just have to go back and fix the things, the formatting and other issues that are identified in the comments on your submissions.
Okay, awesome. Thank you so much.
Okay. All right, everybody. Bye now.